So I just did this video on QCD, and to prepare, I reread this lecture by Richard Feynman about QED, and there was a quote on the first page that really jumped out to me that I want to read to you now. Let's see. Okay, you ready? Okay. What I'd like to talk about is a part of physics that is known rather than a part that is unknown. People are always asking for the latest developments in the unification of this theory with that theory, and they don't give us a chance to tell them anything about one of the theories that we know pretty well. They always want to know things that we don't know, so rather than confound you with a lot of half-cooked, partially analyzed theories, I would like to tell you about a subject that has been very thoroughly analyzed. I love this area of physics, and I think it is wonderful. Isn't that really nice? I've been thinking about it because often I get these emails where people are like, hey, Angela, there's a physicist who has a theory on the cosmological implications of retrograde hairless black holes. You should talk about that. Or, hey, Angela, there's a postdoc in Barcelona, and she's convinced that the perfect dark matter candidate is a quasi-dimensionless holographic crystal. You should do a video on that. I understand. I think I understand that people want to hear the most exciting things. I would argue that those theories that the community has decided are not very interesting or good because the papers have 0 citations are not the most interesting. I would rather talk about the lame things in physics that work. So that's what you're in right now. You're in a video about 10 lame physics things. Surely you would rather watch a video on 10 lame physics things than one by that guy who's like, what if gravity, but it's just electricity, right? Surely. This is a good idea. Number 10, light time correction. So light time correction is just a consequence of light traveling at a finite speed. So that means it takes time for light to be emitted from an object to be received by, a telescope or a human or whatever. Here's a little cartoon I've got for you. Here's a star, right? Stars travel on orbits in the galaxy. So imagine as time moves forward, this star will move up this black line. However, it's also a star, so to first order it's spherical and it's emitting light in all directions, right? Let's concern ourselves with only the light that is moving towards us. This little icon here is what people draw on blackboards when they're doing physics problems, and I always thought it looked like a telescope, but it's actually like an eyeball. So some of the light from this star is moving towards our little eyeball, right? As time moves forward, that star is going to move along its orbit, but also that light that was emitted is going to keep moving towards us. It takes time, right? Eventually, that light will hit our eyeballs, and when it hits our eyeballs, we will see that star in that position that it was when it emitted that light. But in real life, that star has moved across the galaxy. Right? So that is the light time correction. If you're writing your little ephemeris log of what stars or what planetary bodies or whatever are where, you have to account for this. This idea was first demonstrated in the late 1600s. I've pulled up the journal article about it. What this guy did was he looked at the eclipse of moons across Jupiter from 2 different positions in Earth's orbit, so different months of the year. In one, we are moving towards Jupiter, and he counted how long it took the eclipse of the moon across Jupiter, and then a few months later he did it again, this time when we're moving away from Jupiter. And because light takes time to travel a distance, when we are moving away from Jupiter and we are farther, the eclipse should last longer. And he measured that effect, and that's kind of fun. It's kind of fun that you can still read this paper too. Way back when they were typing the long S as an F and the short S as an S. So you can see it says like philosophers, and then science is just regular science. I also like the way it's written. Here's a quote from it. Yet doth it not follow hence that light demands no time. Like, just tattoo that across my face. That's fun. On the planetary scale, Jupiter is very, very far away from us, right? But on the scale of the universe, Jupiter is really close. So he also does this a bunch of times, and he compiles a bunch of different eclipses, so you can kind of get the average time it takes when we're moving towards Jupiter and the average time when it's moving away. And that's kind of fun, just like doing statistics, because it's really not that big of a difference, but it's enough to measure how long it takes light to get to us. For example, the sun is 8 minutes away. So when we look at the sun, well, don't look at the sun. When we see light shining down on us, we're seeing light that left the sun 8 minutes ago. And of course, there's the quantum mechanics about how long ago those photons were made, but we're not talking about that. We're just talking about travel time from the sun to the Earth. That's kind of interesting. And this is what people are talking, or astronomers are talking about when they talk about like look back times. Like when you look at objects that are very far away, you are looking at how they looked when they emitted that light. So the farther away you look, the younger the objects are that you're looking at, which is how you get headlines like astronomers see crazy young galaxy, cosmological crisis, ? Is silly stuff. But that's what the Hubble Deep Field does. So you choose a dark area of sky and you just open your telescope bucket to catch all of the light, and it catches light from super far away. So you see super old galaxies, and that's actually really handy because we only have one universe. We can't like test any other universes. So it's nice to be able to look back in time essentially and see how the universe evolved. Number 9, talk tubes. I said these were lame, right? This is like a playground toy. I am shocked by the price tag. I could set you up with a talk tube for $400 easy, but what they are is a little speaker and a tube that goes underground, and they put a second speaker like hundreds of yards away in the playground. If you imagine 2 children yelling across 100 yards in a huge packed playground, they couldn't hear each other, right? Like the sound would be damped by all the stuff in the air and the medium, like all the trees and the playground materials, but also all the screaming of the other children would prevent that sound from reaching the kid. So they have these little tubies. One can like whisper into it and the other kid puts their ear and they can hear it. Because the tube acts as a type of waveguide, an acoustic waveguide that traps the sound waves and just carries them all the way to the ear. And I think that's really fun. The idea of a waveguide is a physics principle with applications all over. But I really like these little talk tubes, especially their place in history. If you think about when the telephone was invented, manufacturers couldn't really keep up with the demand for telephones, so there was a very brief period where people would come install talk tubes in your house and they'd be like, it's just as good, right? Except it's not just as good, because where telephones can call any number of places, talk tubes only work where the tube is pointed. So I found this really funny picture of this office where this guy has like 8 talk tubes and they all go to different rooms, and you would like pick the same one and you would like holler into it so they could hear you. I think that's very funny. I like the idea of a talk tube. But like I said, it essentially traps the sound waves so the data can be accurately carried over longer distances, and you can hear the data that was transmitted over this long distance. But this also works with electromagnetic radiation. Waveguides work for like optical wavelengths for data transmission and stuff. But there's also one in your microwave, which I think is very fun. So here's a diagram of a microwave. You have a power supply, which is powering a magnetron, which makes microwaves. Because the way a microwave works is it shoots your food with microwaves at a very specific frequency, which will vibrate the water, which will release energy as heat, which heats up the food. Right. So the magnetron makes the microwaves, but you don't want the magnetron in the microwave cavity where your food is, because if you get oil or food crumbs in that means you're going to have a fire. So instead what they do is they attach a waveguide to the magnetron, so the microwaves get made and then they get trapped in the waveguide and they travel to the open cavity of your microwave. And sometimes there's a little fan there that's made of metal, so when the microwaves hit it, they kind of bounce around in all directions in the microwave, heating your food evenly. But if you open up your microwave, you'll see like a little plate that's made of mica, and this allows the microwaves to come right out. So the waveguide acts just like a talk tube, but for microwaves, and it pushes the microwaves into your like microwave cavity to heat your food. Number 8, solar cookers. And I didn't realize I was talking about food again, but I really like these. So these are just parabolic mirrors. They catch the light in all direction, and then the mirror is shaped so that the light is focused on a certain point. So if it's an 85-degree day, it's pretty hot, but it's not hot enough to like cook a soup. So what you do is you put your pot inside this mirror, the light is focused onto the pot, and it can heat your pot to very high temperatures. Like you could bake a bread in one of these things, get it up to 550. I really like this idea as a way to cook because it's totally free, right? Like mirrors work for free. You don't need to power those bad boys. So you take the light that's going to be there anyway and you just focus it onto your little cook pot and it works. It's beautiful. Of course, harnessing the power of the sun can be difficult because sometimes it's cloudy or maybe you don't get as much daylight in certain places. But I do think it's really interesting to be aware of these things, just in case, like societal collapse and you can't power your traditional oven. You could just make a solar oven. That's kind of fun. But also, these things kind of work like death rays. You've probably seen a cartoon where the kid who's supposed to be evil is like taking one of those glasses and just popping to death the ants. There's this really fun historical story where Archimedes did this in the Battle of Syracuse. He has all these soldiers standing on the coast with mirrors, and he's like, great, we'll all point the light at the sail of the ship and they'll catch on fire. Haha, they can't come fight us if they're dying of fire and drowning in the ocean. And I really like this story as like harnessing the sun for a weapon. That's kind of fun. But also because this story is one of the most debunked stories in history. Like, here I am, a modern day YouTuber debunking fluoride haters. In the 1600s, you had Descartes being like, I don't think this would work. Archimedes is a liar, building little models and being like, this doesn't make sense. And really, Archimedes didn't even talk about this. It was Plutarch, that one historian guy, but he's like 200 years after Archimedes, so how is this even a debate? But really, it's a debate because it sounds really cool. It seems like it would kind of work. We've all seen a solar cooker. It could probably work, and it sounds cool, right? But of course, the debate continues, and Mythbusters did it. Actually, they did it twice. The first time they were like, LOL, absolutely not. And then this group of college students did it for like a little project and they were like, haha, we actually did it. So they did it again and it didn't work again. It like just requires too many things to be in perfect conditions. Here's a little clip.
All to aim your beams at that black sun and keep them as steady as possible. Are you ready? We are doing this for Syracuse in 3, 2, 1.
If this was a real war, you just lost, because I got a whole bunch of you guys, and you didn't get one of me.
I think you're right.
Man, do I miss Mythbusters. That was such a good show. Is there a science show like that exists? What app should I get to watch good science shows? What replaced Mythbusters as like a really fun like engineering show? I remember like a solid Friday night for me would be watching a Mythbusters or a How It's Made and just like enjoying watching engineering on TV. I feel like we don't have that anymore. That sucks. Number 7, the triboelectric effect. So the triboelectric effect is when you can rub two materials together and exchange charge. It's responsible for the vast majority of like static electricity, although the only reason I say vast majority and not all is because this is the internet and there's like one other way to do it, but like whatever. There's this great demo on the University of Colorado Education Physics website where you have John Travolta like rubbing his foot on carpet and the charges build up and then he touches a doorknob. The triboelectric effect is great to demo if you're trying to show that charges exist, that subatomic particles are like real things, and that's why I like it so much. But for me personally, I have this very like formative experience in my like educator career where I was a sophomore in college, and so I had only had like one physics class, and I was doing a demo type thing for the chemistry club at an elementary school, and my job was to have the Van de Graaff generator, and these groups of like 5 fourth graders would come, and I would just pick the one with the longest hair and make the hair stand up and be like, what do you think is happening? You know, that standard demo. So I get the first group of kids and I pick the boy, it's the boy with the longest hair, and nothing happens. And I'm like, oh no. And so I go find the professor and I'm like, nothing's happening. And he's like, oh, it's because it's humid today. Like in Rowan County, Kentucky, it's Appalachia. It's just a rainforest, right? It's super humid. So he was prepared for this and he had a hairdryer. And I took like the ball off and like you open it and there's like a belt. And the belt is the thing that moves the charges to your little ball. So he was like, just heat this up until the water has evaporated off of it and this thing will totally work. So I told the kids to move to the next station and come back around and we would get to do it later. And then after that, because I got rid of all the water on the belt, it worked perfectly and I did the little demo. And then the group of kids comes back and the little boy with long hair comes up and he sticks his hand on and his hair stands up and I'm like, what do you think is happening? And this other little boy who's probably, this was 12 years ago, so this kid is probably like a professional scientist now or something. And he was just like, well, it has something to do with heat. And I was like, huh, why would you think it? It's not too hot today, and there's electricity coming through it. And I was like, hey, is it hot? To the little boy touching it. And he was like, no. And he was like, it has to be heat. And I was like, what do you mean? And he was like, I saw you using the hairdryer on it. Like, I saw you blow drying it. You heated it up to do this, right? So maybe it's like that is hotter than the hair. And I was like, wow. He taught me a very important lesson, which is that if you do a physics demo and it fails, you can't just do the demo again and be like, see, physics. You have to explain why it failed. And in this case, the triboelectric effect is dependent on not only the materials, but also the humidity. Because if you have water in the air, it's going to break your little circuit. Whatever is moving charge across it, it is going to be broken by the water molecule, which is conductive, right? So you have to dry the little belt to make this thing work. It's not about heat so much as how much water is in the air. Number 6, granular convection. So this one is one of my favorite things to talk about. It's because I'm super cool and fun. It's also called the Brazil nut effect. If you imagine like a dad, do you know dads? Like they're sitting in their chair, they're watching The Patriot with Mel Gibson, and they have like a can of nuts. Right? So they pick up the can of nuts, it's mixed nuts, and they shake it, and they look for like the almond, and they eat it. And then they shake it, and they look for a pecan, and they eat it. Would you have almonds and pecans in the same mixed nuts? It doesn't matter. Anyway, what happens when you shake it is that a convection style, like current almost, happens in this little system, and the big nuts go to the top, and the little nuts go to the bottom. So that's why 2 days later, he opens the can and all the Brazil nuts are on the top, and he's got to shake it again to look for the little nut. This also happens like with cereal. You open your Honey Bunches of Oats and all the big pieces are on the top and the bottom is all crumblies. You open a bag of Doritos, all of the biggest chips are on the top and the bottom is just the tiny little pieces. It's the Brazil nut effect. You might expect that like Brazil nuts, they're more massive because they're bigger. They should fall to the bottom. What actually happens is like you're transporting the cereal and the box is getting shaken up, or you open the nuts and you shake it to search for the specific nut. You're creating these little air pockets, right? The smaller pieces can fit into those air pockets and fall down, and the bigger pieces cannot do that. So they are just left on the top. The more you shake it, the more it gets sorted. So it does make sense. I just love those little physics things where like you can see someone doing the thing in real life and be like, you know why all the Doritos are broken on the bottom, right? But wait, there's more. In the early 2000s, this research group theorized, it's Hong and Quinn. Their paper is called Reverse Brazil Nut Problem, Competition Between Percolation and Condensation. The reverse Brazil nut problem. They theorized that exists. They said, you know, whenever we see the Brazil nut problem in real life, it's always with similar density objects. Like the Doritos all have the same density because they're made of the same thing. Nuts have similar density. But what if the smaller objects are more dense than the massive objects? Wouldn't you get the reverse effect where the big guys go to the bottom? And they theorized this, and then a couple years later, in a paper called Reversing the Brazil Nut Effect, Competition Between Percolation and Condensation, let's ask Emily Post if it's appropriate to just steal the name of a paper without referencing the authors in the abstract or title. I don't think so. But anyway, they ran simulations and they built specific density objects and they tested it, and it's true. So it turns out you can get the Brazil nut effect, or depending on your objects, you can get the reverse Brazil nut effect. So if there's ever a situation where you specifically want everything to stay mixed, you can kind of toggle those two parameters and get a mixed thing, or you can force it to have the Brazil nut effect or the opposite. This type of thinking is really important in astronomy. Like if you're thinking of how you build up a planet or any body, even an asteroid, from like pebbles and little bits of dust and gas and stuff. It's also really important in concrete manufacturing, which is one of my special interests, but that could be a different video. Number 5, a wedge. Honestly, I could have put all of the simple machines, just like 6 of the 10 things in this list of 10 things. I could just have simple machines. I think simple machines are so interesting because they're this ancient technology that everyone knows should work, but they're based on physics principles which you can quantify and qualify and evaluate, and isn't that very fun? So a simple machine is a device that uses leverage to multiply force. So the idea is you are doing the same amount of work but expending lower energy. So it makes the act of physical labor easier for the humans who have to do it. A wedge might be the simplest one. The easiest thing to think about is like an axe. So it's like an isosceles triangle almost, and you can think that you take your axe and you slam it into the piece of wood and you are applying a downward force, but because the wedge gets thicker as you go up, that is pushing outward into the wood, which splits the wood for you and get those nice even cuts. So it lowers the work the human has to do to split the wood into nice manageable pieces. Another type of wedge is a doorstop. I said they were lame. I know I'm holding up a picture of a doorstop. It's totally fine. Imagine a doorstop just on the floor. You can kick it, you can pick it up, it doesn't weigh anything. It's totally easy and fine. But when you wedge a door onto a doorstop, it's hard to move, right? The wedge is stuck. That's because the force of the door pushing into the wedge applies this backward force to the floor from the wedge, which increases the friction, which means it holds the door open no matter how heavy the door is. Also, if you're one of those people who like satisfying videos, you can use something called a plug and feather wedge to split like tons and tons of quartz into these nice pieces that can be used for building or making countertops or whatever. I'm sure you've seen this, but the idea is that you have this thing that weighs 10,000 pounds and you can't like chop it and you want it to break nice and even. So what you do is you drill holes across the body 6 or 8 inches apart and you input these plugs, and the plugs have a little break in them. So when you take your wedge and you hammer it in, the plug applies that outward force. And so to break this huge block of stone, you're just like tapping every 6 inches. You have to wait because you're putting a bunch of pressure on it. You have to wait for the pressure to equilibrate, and then you tap, tap, tap again. You wait, and people can tell from the sounds what is happening. I'm hopefully playing a video while I'm talking about this. And one human with a single hammer can break these huge stones apart. It's amazing. It's so cool. Number 4, probability. Probability is a huge topic in physics, but I like to think about it in just the terms of how we give answers to physics questions. I think that's a really fundamental idea that people often skip. Imagine I'm holding 10 grams of cobalt-60 in my hands. I wouldn't recommend it. It's radioactive, but imagine I was doing that. I can tell you matter-of-factly that in 5.27 years, I will have 5 grams of cobalt-60. If I'm holding instead a single atom of cobalt-60 in my hand and you said, "Hey Angela, when will that decay?" I can't tell you an answer. I don't know. I can't even tell you using the half-life. I can't tell you, hey, within 5 years there's a 50% chance that it will decay, because that's not exactly true, because the process is completely random. If you asked me, when will this decay? And I said, well, the half-life is 5 years, so maybe within 5 years. And then you ask me 3 years later, and I'm still holding that same atom, I would say, well, the half-life is in 5 years. Maybe within 5 years. And you would say, but we just did 3 full years. And I would be like, well, yeah, the past history of this atom doesn't affect the probability of when it will decay. It's a completely random process. Of course, a physical thing happens when something decays. It's got to do with random fluctuations in the vacuum or whatever, but we don't control that. We can't predict it. We don't know when or where it will happen. The only reason I can tell you for the 10 grams is because of high number statistics. 10 grams of a thing is like Avogadro's number worth of particles, right? Versus holding one particle in your hand. With that huge number, we can do statistics, and we can say, on average, they do this in 5 years, so we can accurately predict when you will have half of it. But when we're holding one atom, I can't sit there and tell you, well, April 27th at 4 a.m. That's not how it works. Like, the only thing I can tell you is that I know the probability of an event, and here is that probability. But I can't tell you when it will happen. I can't force it to happen. Isn't that interesting? Isn't it interesting how you can't answer the question? I think it's really important to think about that when you're answering physics questions, especially when you talk about quantum. But also, I find it interesting how people don't like that. People really want an answer. And with classical physics, like if I'm holding a ball and I ask you how long it would take to hit the ground if I let it go, you can just measure the height and you can tell me. But that's not the case with quantum mechanics. I can only tell you these are the options and these are the probability of each one. And those probabilities are maintained until something happens. It makes me think of engineering. Now, I am not an engineer, but I'm going to recommend an engineering book. If you're an engineer, tell me if you hate this guy or whatever. But I really like this book. This book is probably older than me. It's called To Engineer is Human: The Role of Failure in Successful Design. And it's a really fun read. At the very start of this book, he talks about how he teaches failure rate to his new engineering students. And he does it with paper clips. And he gives everyone paper clips. And he's like, twist it as many times until it breaks. And then tell me the number that it took to break it. And then he starts plotting it on the board like a little histogram. And of course he gets a Gaussian distribution. Like sometimes it takes 2 twists, sometimes it takes 25 twists, and there's like a peak around some value. And I think this is really interesting because this is how I feel engineers think. Like you can never get an answer from an engineer. If you ask an engineer to build you a little device for your lab and you're like, hey, how much weight can this hold? They'll just be like, well, what are you putting on it? How long is it staying there? Is it running while you're doing that? And they'll never give you a straight answer. How often should I clean this? Well, what's getting on it? Why is it dirty? What do you mean? I love engineers, but that's always my experience with engineers. Like, how long can I use this paper clip? And they're like, well, at what angle did you bend it? What force were you using when you bend it? What is the history of this product? How long have you been bending it? And they can't give you an answer. That's because the world works a lot like quantum mechanics. Like, you don't know the history of a thing. You don't know if everyone's going to use it appropriately. You can't just answer the question. And when you're an engineer, you're kind of responsible if you give a bad answer. And so they're always like couching their answers, and I love it. I love engineers. I was actually going to do this as like a little demo for you, but all I could find were these stupid plastic coated paper clips that won't break. So anyway, I recommend this book. Number 3, bar formation. So there's this thing that goes around Reddit sometimes that's like, what could you talk on for 2 hours with zero preparation? And I feel like everybody with a PhD has an automatic answer to that question. I studied bar formation and the interaction with dark matter, so I could talk about this for days and days and days, but I won't, because I only want to talk about how there is a bar instability that is caused by gravity that makes things turn into bars. If you've ever seen a picture of a galaxy like this, that thing in the center is a bar. It means that at some point there were stars on circular orbits, and then something caused them to turn into a bar shape, and now those stars are trapped on a bar-like orbit. I have a GIF that's showing that. In the yellow, we have a disk of stars. They're all in circular orbits in a little galaxy, and the aqua guy is like a little perturber that goes around, and you can see at the center of that galaxy, you get a bar shape. This is the thing that actually happens in space. That's kind of fun, but it turns out it's purely a gravitational interaction. So if you think of like the gravitational potential as a tensor, have you guys noticed people are being really weird on the internet about gravity lately? Like, gravity is not a force, actually, and it's not a video for today, but it's kind of interesting how like you can just redefine how you're talking about a problem, and then people act like this is the correct answer, even though it has to give the same answer. Because that's what we observe. It doesn't matter. But if you prescribe to relativity and you know that you can describe the gravitational potential as a tensor, if you have like the Earth-Moon system, you know that because of the gravitational interaction between these objects, the Earth is pushing towards the moon, but also on the other side, the Earth is being pushed away from the moon. That's what happens to these orbits. At the center of your galaxy, you have a nice little circular orbit, and then something flies by, it pulls the orbit in this direction and in this direction. So all the stars go from happy little circular boys to even happier bar boys. And I say even happier because this orbit is a lower energy orbit than a circular orbit. So this makes them happier because things just love to lower their energy. You can't stop them from doing it. They love to do that. So once you have the bar, even if the thing perturbing it flies away, you got a bar forever. That's why you look out at disk galaxies and like 75 to 85% of them are barred. It's just a happy lower energy state. And it's a purely gravitational interaction by like a tidal flyby. But you know what? It doesn't Doesn't even have to be a tidal interaction. An isolated disk, just stars hanging out, will just eventually develop a bar. That's cool. This is the exact same mechanism that causes the tides, right? Like if you imagine the Earth, hopefully there's a GIF right here, and one side is pulling towards the moon and the other is pushing away. That's why you get tides. You get high tide every 12 hours. If gravity wasn't described as a tensor, then you would only get tides every 24 hours, but we don't. We see it every 12 hours. And this is another way people are weird about gravity on the internet. Has anyone noticed this? If you Google what causes the tides, you'll pull up a little Quora forum and somebody will be like, oh, it's gravity. And then someone else will be like, no, it's tidal forces. Tidal forces cause the tides. Gravity pulls the moon and the Earth together, but tidal forces cause the tides. And it's just like, babe, that's also gravity. Gravity is tidal forces. What do you mean? You're acting like it's a different what? But anyway, if you would like the definitive answer to what I talk about when I talk about gravity, here's the book. It's coming in 2029. Please buy it. I have to sell it to a company who will print it first, but after that you can buy it. Thank you. Number 2, faster than light velocities. So you know that nothing can travel faster than c, except stuff does all the time. It's totally fine. Here's the trick. There's like a little trick to it. So if you imagine you have a wave, like a sinusoidal wave, it looks like this. The velocity of that wave is called the phase velocity, right? But you cannot transfer information with like a single sinusoidal wave. You need a little packet. So you have a bunch of sinusoidal waves, and they're clumped as a packet, and the velocity of the whole packet moving is called the group velocity. Usually the phase velocity can go faster than c, and that's totally fine, but the group velocity doesn't go faster than c. Usually the group velocity, the wave packet, is traveling at the group velocity, and that's what's carrying the information, so that can't go faster than c, except there are these very clever scientists who have built, it's waveguides again. I've already talked about waveguides. They've built these materials that can attenuate the wave packet to do really interesting things. Here's a fun little paper about it. You can make the group velocity inside a material move slower than c, called slow light. You can make it move faster than c, called fast light. You can even make it have a negative velocity. That's kind of interesting, right? The trick is that no information is being transmitted, because you can never have information or energy travel faster than c. So when they say nothing can be faster than c, the actual physics thing is about causality, which means like if I am sending information and a person is receiving it, that information cannot travel this distance faster than the speed of light in a vacuum, okay? If it did, that would break causality, which would mean that there is some reference frame where this person receives the information before I have sent the information, and that cannot happen because that would break physics. So these scientists are making these really interesting materials that kind of work around that rule but do not transmit information faster than c, because that would break physics. And they're kind of just like, now the fun part of finding a use for this material, which I think is really fun, because that is the fun part. They've done a thing, and they're like, what are you going to do with it? What is it useful for? What an exciting idea. What an exciting time. Number 1, outgassing and the vacuum impossibility. So imagine for a fundamental physics experiment you're doing, you need a vacuum chamber. Why would you need that? I don't know. Maybe you want to study low pressure plasmas. So you need to make a vacuum so that it's in a low pressure, right? Because PV equals nRT. So if your N is very low, meaning you don't have a lot of stuff in there, number density is low, your pressure could be low, and you can look at your low pressure plasma. Maybe you want to study a molecule independent of collisions. So you want to make the mean free path really big or really small. You don't want a lot of stuff in there so it doesn't collide with other stuff. So you can just look at that molecule. Or maybe you do want it to collide with stuff. Maybe you want to study a very specific interaction between two guys. So you want to control the path they travel on. So you make a little vacuum. There are thousands of reasons you would need a vacuum chamber. And that's where we talk about outgassing. Because if you've made a vacuum chamber, it's on Earth, it's made of some material, right? Like you got steel walls or something. The steel walls will be touching the vacuum, and when materials are in the presence of a vacuum, they start outgassing. any gas that was trapped inside of that solid material will just spontaneously move into the vacuum. And this is bad, right? Because it could contaminate your sample, right? Like if you're studying a very specific material and then the steel just starts shooting carbon dioxide or something into your vacuum, it could damage your sample. This will also change the pressure inside the vacuum, right? Because if you have a vacuum chamber, like you're never going to make a perfect vacuum, but you have a really nice vacuum and there are like order 100 or 1,000 particles inside of it, and then all of a sudden the walls start outgassing gas, you've doubled the number of particles. The pressure has skyrocketed in this little vacuum chamber. So your experiment has to be started over. There's also a thing that can happen when, if the material is outgassed, it can condensate on the walls of your vacuum chamber, which will mess with your measurement devices, which are usually like stored on the walls, which is a huge problem if you're trying to measure something with precision physics. And finally, if you have stuff outgassing onto your vacuum, you no longer have a vacuum. It's just no longer a vacuum chamber. Your experiment has failed. You have to start over. You can track this by taking a mass spectrometer and sticking it into your vacuum chamber, and it will tell you like what molecules are being outgassed, or maybe if you have a leak, like the box isn't good enough and so you can tell what's getting in. If there's some dumb human who touched the inside of your vacuum chamber and now it's got fingerprints on the walls, you'll see the mass spectrometer reading a bunch of hydrocarbons and stuff. You can source the problem by using a mass spectrometer, but once you eliminate everything besides outgassing, you have to start thinking about what materials to make your vacuum chamber out of. And NASA has like a document, it's free for everyone in case you want to build a vacuum chamber, that talks about what materials are good for what kinds of experiments and what type of outgassing will happen. And this is of course because in a lab on Earth, you want to keep a vacuum and your outgassing is going into your experiment. But in space, it's kind of the opposite problem. You build a little satellite or something, or a little probe, you send it to space, which is essentially a vacuum, and your probe, whatever it's made of, starts outgassing. This was actually a problem, I think, with Cassini, the one that went to Saturn. Something outgassed and then it like formed a condensation on like the camera, which is real bad if you're sending a thing all the way to Saturn. So that's why NASA cares about it. I think the resolution was they heated it up and the condensation went away and then the camera worked. But you can understand why NASA cares about it, but it's kind of the opposite of why a atomic physicist on Earth would care about it. Once you've done that and you have the super nice materials, you kind of just have to continually pump your vacuum. Your vacuum will never stay a vacuum on Earth, and that's why I called it an impossibility, because you have to continually run your pump in order to maintain a vacuum because stuff keeps getting in there. And of course you can do an experiment, but the vacuum is impossible on Earth. I know what you're saying now. Angela, cathode ray tubes are vacuums and those last for decades. What are you talking about? First of all, great point. Second of all, I cannot say cathode ray tube without thinking about Hadestown. But yes, a cathode ray tube is a glass with a vacuum inside of it, right? And glass will outgas just like all other materials. So how do you fix it? It's actually really fun. It's called a getter. So you have your glass. You put your getter inside, and it's usually like a block of barium or something, and then you make your vacuum and you seal it, and then you activate the barium, which is usually just like heating it up. And now, when the glass starts outgassing into the vacuum, the barium gets it and then chemically combines it with the little barium block. So it's not in the vacuum, and that's really fancy, and it totally works, but it's just not what you want to do in a like high precision atomic physics experiment, because the barium can interact with your other stuff. You don't want to put stuff in your vacuum, but it works perfectly for something like a cathode ray tube, which maintains its vacuum ability, vacuumness, the vacuum, it maintains the vacuum. End of video.